So hi, I'm Cliff Anderson. I'm the Associate University Librarian and Professor of Religious Studies, and I want to talk to you today about a learning opportunity related to a programming language that we teach in the library called xQuery. So you can see the details here, but why would you want to learn xQuery? So xQuery is really good at analyzing semi-structured data. So for example, if you have large corpora of documents and you want to look at relationships in between those documents, you don't want to just turn them into like a bag of words and look across the whole corpora, but you actually want to look at perhaps interactions inside of those documents, then xQuery is going to be the programming language you want to use. We teach this working group that meets every week during the semesters at 3 o'clock on Fridays. And what we work on is teaching not only the basics of xQuery, but also the sort of tool set that you use for doing these kinds of analyses. So we teach XML databases. We also teach how to develop data-driven web applications based on xQuery and the data that you model. The ranges of use are really wide. We have linguistics in our group, linguists in our group. We have people that are doing biology. We have people that are in accounting, and we have people that are doing theology. So it really ranges. Anyone that's working with documents, I think, might want to take a look at this technology. And we have 2 learning tracks, so people can join anytime. We have a kind of basic learning track where we give you simple problems that based on the sort of 99 problems tradition, which started in various programming languages like Prolog. And then we have a more advanced track if you've been there for a while. So all I want to say is, hope you'll join us, and thanks for letting me give that pitch.
Hi, I'm Gayatri Narasimham. I'm the Associate Director at the Vanderbilt Institute for Digital Learning. This past year, we've been having a data visualization working group, which is an informal group of faculty, researchers from different departments in STEM and humanities disciplines. So the goal of this group was actually to bring together researchers from these different fields and talk about data visualization and actually learn some different tools. So we've been exploring Python, R, Plotly, a bunch of tools, Tableau. So just looking at visualizations and how do you make visualizations with these tools. Clearly, you need to have some data already with you. The abilities to actually convert your data into a form that can be visualized. So we weren't exploring too deeply into those aspects, but actually the tools itself, how do you create the visualizations? And every month, we met monthly, and our presenters would walk you through the programs that they used and the step-by-step instruction for creating these visualizations. Just as an example, here are 2 different forms for representing the same data, which is actually about questions that on the forum, which was taken at the time. So this one is a box and whisker plot to get responses on the Stack Overflow forum for questions related to Python or Plotly or Tableau, and the other one is a word tree. So 2 different ways of representing information. So it's an informal group. Again, if you have any questions, please ask me or just email me. Thank you.
Hello, my name is Hiba Baroud. I'm an assistant professor in civil and environmental engineering. My work is at the intersection of data, risk, and humans. Primary interests are in developing predictive analytics models and decision methods to understand how infrastructures and communities recover after a disaster. I could have situations with large data, small data, and sometimes no data. And I have to work with all that. So I'm showing an example here on the slides of one method that we're developing in my group called hierarchical Bayesian kernel methods, which works really well in situations where you have clusters with a lot of information and others that have not much data to produce these accurate predictions. We are applying it to measure the recovery rate of communities from power outages. And the ability to predict this rate would help utility companies allocate resources before, during, and after a disruption. So the ultimate goal of measuring or making those predictive measures for risk and resilience is to use them as an input into an optimization framework and a decision model to be able to allocate those resources for both the infrastructure and the communities. And I didn't get the sound, so that's good.
My name is Andreas Berlind. I'm a professor in physics and astronomy. And I'm an astronomer, which is a field, astronomy is a field that's really flooded with data, both from observations of the real universe and simulations of fake universes that we make. So I'm going to try to explain the whole universe to you in 60 seconds. So on the observational side, which is the top part of the slide, we start with telescopes, like that one in New Mexico. We make maps of the sky that contain on the orders of hundreds of millions of galaxies that we observe. And then we do more detailed measurements of the galaxies, which are the little boxes with those plots there, which are spectra. And those tell us the distances to the galaxies. So then we make three-dimensional maps of the galaxies. And then we quantify the spatial clustering of those maps to measure some statistic. And there are many ways you can do this, which is down here. So then we want to say, what does that teach us about the universe? Well, to do that, we need to model. And so we start with supercomputers. We run really expensive n-body simulations that describe how dark matter evolves in the universe, and these typically have tens to hundreds of billions of particles, and you're calculating the force of gravity among all the particles. That's really hard. To do that, you need to assume a cosmological model, which is the big numbers we want to know. What's the mass density of the universe? How old is it? What is dark energy? What's dark matter? Stuff like that. And then we need a model of galaxy formation to decide where galaxies will form in that grid to make maps of galaxies that we can then compare and rule out the model. So my big holy grail is I want to know how to run this thing that takes several thousand hours on many thousands of CPUs, how to do that really quickly so I can put it in the loop of my big Markov chain and constrain my cosmology parameters. So if any of you geniuses knows how to take a simulation and predict what it's going to give you without running the simulation, that is my holy grail. So that's what...
Hi, everyone. I'm interested in using the genome to connect your gut with your health. And so I look at the human microbiome, which is a complex and constantly changing community composed of thousands, trillions of different microbes from thousands of different species. And it's a genetic repertoire that outnumbers our own 500 to 1. And we can look at these communities and assess changes in microbial variation and the community structure itself. Now, using genome-wide association studies, we can draw conclusions between the genome, or your genetic variation, and changes in these communities. Now, there's a wealth of new data sets that are available to do that. But does this matter? We can also look at human genetic variation in biorepositories of DNA and electronic health records, like BioView, which people have mentioned earlier. And we can look at disease outcomes related to that genetic variation. And so using BioView, we can look at the genetic variation that we found to relate to the microbiome and ask the question, does it relate to disease? All right. Thanks,
Filtergraph is a web-based data visualization service that anyone can go and upload some data and get back all kinds of nice charts and graphs based on the data. It is interactive. As you change settings on one side of the screen, it'll affect the graph on the other side of the screen. You can build scatter plots, histograms, tables, and world maps, and you can filter the data. You can highlight various points in the data. It is easy to use, and it is designed for speed. You can build 3 million points in 2 seconds or less. You can share a link using a button on the screen and send it to someone else, and not only do they see what you're seeing, it's within the graph itself. It has been used in nature caliber research as well as space telescope design and exoplanet hunting and autism research and data journalism, and 1,000 people use Filtergraph around the world. If you are interested, you can create an account at filtergraph.com. I'm Dan Berger. Thank you.
Hi, I'm Jordan Everson. I'm an assistant professor of health policy. So there's ongoing concern that the healthcare delivery system is fragmented, such that when patients move between locations, information about their care doesn't follow them, and care coordination suffers and quality suffers. We sought to understand this using a network analytic approach. So we first defined hospitals as the nodes in these networks, and then the shared patients moving between hospitals as the weighted ties connecting the networks. To get to structures of a network we could measure, we first defined local, kind of dense subnetworks in this overall national network using community detection algorithms, resulting in 120 communities of hospitals across the country. The real question here is, what structures of these networks are protective from this fragmentation of care? So to do that, we looked at hospital performance on readmission rates and spending per beneficiary and different network structures, and found that more concentrated networks, that is, networks where hospitals share a larger proportion of their patients with fewer other hospitals, had lower rates of readmissions and lower spending. We also found that more centralized networks, networks that look more like a hub and spoke model with a core, maybe academic medical center in the middle and community hospitals referring patients there, had lower rates of readmissions. So I think this points to a couple of interesting network structures. The next question is, can public policy do anything about these structures? And in a follow-up study, we found that indeed accountable care organizations create more concentrated networks of hospitals.
Good morning, everyone. My name is Wil French. I'm with the Advanced Computing Center for Research and Education, or ACRE. I'm going to try really hard not to come off as a car salesman standing up here, but I apologize if it comes off that way. My goal is just to provide a brief introduction to ACRE and to make you aware of some of the infrastructure that can be leveraged to perform some of your scientific computing and data science-oriented applications. We manage a supercomputer composed of over 7,500 CPU cores and about 120 NVIDIA graphics processing units. We also have over 5 petabytes of disk space. And so this just gives you a taste for some of the resources that are available for your applications. One of the main goals of ACRE is to relieve researchers of the burden of things like systems administration and software installation and things like that. Generally, researchers are not computer nerds per se. Everyone at ACRE is a big-time computer nerd, and we love systems administration and installing software for you. So please let us do that for you. We have an assortment of data science tools. Some of the old-school high-performance computing tools like OpenMP and MPI are available, but we also have a Hadoop ecosystem available that gets used widely in the data science industry, so you have access to tools like Spark and Hive, and there's lots of other tools with very cute names like that in that ecosystem as well. So yeah, I'll be around all day today. If you have any questions or want to chat, let me know.
Hi, I'm Jake Huey. I'm an assistant professor in biomedical informatics, and my lab's really interested in systems with lots of moving parts. And the key word is moving because it's the dynamics that change over time that really fascinates us. One example of that is circadian rhythms. And circadian rhythms is based on the idea that you have molecular clocks throughout your body. And these clocks synchronize themselves to day and night and coordinate daily rhythms in your behavior and your physiology. And actually, this image on the left here is a cryo-electron micrograph of the circadian clock in a cancer cell. No, I'm just kidding. But that's one of my favorite paintings. But in any case, there's a lot about circadian rhythms we don't understand, and we do not use our knowledge of rhythms very well in medicine. So the lab's primary tool is computation on diverse large-scale data sets. That's part of why I'm here. And we work hard to make all the products of our research open and reproducible. I just started my lab a few months ago. We are not yet ourselves a system with a lot of moving parts. But if this sounds interesting and you or somebody you know is looking for an opportunity to take some risks, make mistakes, and try to learn from them with the rest of us, then please let me know. Thanks.
Hi there, thanks. Okay, something different. My name is Sarah Igo. I'm from the History Department. I'm also the director of our program in American Studies. And I wanted to use my 60 seconds to talk about two images, the two that are here. And I also hope to persuade you that history has something to do with how we think about data. The first thing I want to point you to is this advertisement here from 1938. Can you see it? The wording on it? A really personalized ring for men and women, which was a Social Security ring, which one could get in sterling silver and have birthstones and so forth, but also one's number prominently displayed. It ran in 1938, and it may seem quirky, but it was not alone at all in the consumer market for products like this. There were, in the 1930s and 40s, lots of consumer products marketed to Americans that broadcast or displayed their Social Security numbers, including watches, luggage tags, wallets, other kinds of jewelry, keepsakes, frosted bronze plates, and the like. So it's striking today, obviously, for the kind of wanton display and broadcasting of a piece of private data, but I want to suggest that things that we think of as private today were not always so, and for good reason. The second image I want to point you to, and I hope you're able to see in the back, is this rather famous photograph from 1939, taken by the photojournalist Dorothea Lange, from 1939 in one of the Depression camps, work camps. This is a lumber worker who had emblazoned his Social Security number on his bicep. Again, a not uncommon practice, not a common, but not uncommon practice in the 1930s and 1940s. Lots and lots of reports of tattoo parlors praising FDR, the president at the time, for instituting Social Security because there was such a large uptick in their business for exactly these kinds of tattoos. I just want to pose the question, how do we make sense of this intimate and kind of public display of what was a bureaucratic ID? And what changed? Obviously, a lot changed, from attitudes toward the state to computerization to change how we think about our Social Security numbers. But it's only by casting off our contemporary assumptions about what is private and what private data might be that we can understand how something like the Social Security number, which was quasi-public and a symbol of economic security, could become a cornerstone of contemporary data insecurity. Thank you.
Good morning, I'm Robin Mace. I have the distinct pleasure of not only being here, but having my dream job as Metro's Chief Data Officer. Just out of curiosity, how many people here are familiar with open data? Oh, good number, excellent. Open government data is a decade-old philosophy and movement that public sensitive government data be made freely available without license or registration for public use, reuse, and redistribution in human and machine-readable formats. The data can then be used internally by government, by residents and businesses to improve and personalize citizen services, participation in services delivery, as well as to optimize operational efficiencies and maintenance, to enhance reporting services, data product development, and to inform and facilitate commercial product development. To wit, Climate Corporation, a digital agriculture company founded in 2006 on open government weather and agricultural data, sold to Monsanto in 2013 for $1.1 billion. Metro Nashville and is proud to partner with Vanderbilt's Visor, ISIS, and a number of other individual departments, researchers, and even student groups, including Vandy Hacks, and most recently Owen Libraries, to drive our smart city research and efforts on Connected Nashville, as Metro's smart city efforts are known. Connected Nashville, indeed all smart cities, are predicated on quality data and robust data infrastructures, from building operations to energy to transportation. Opportunities to transform and optimize operations and quality of life with data and connected devices are here now and shaping our futures. We hope to see you at data.nashville.gov soon. Thank you.
All right, so it's my turn, I guess. My name is Ryan Oakers. I'm a postdoc here at Vanderbilt in physics and astronomy. I want to talk to you briefly about the next generation NASA satellite that's going to be looking for planets, called the Transiting Exoplanet Survey Satellite, or just TESS for short. TESS is going to be looking at basically the entire sky, going to be surveying cool stars, looking primarily for Earth-sized and Neptune-sized planets. Its primary mission has a goal of detecting about 2,000 or so planets. We're expecting closer to about 50K, which would be great. The way that TESS works is it has 4 cameras. It's going to be observing in longitudinal strips, and if you were to put your arm out at your hand out at arm's length and look at sort of the distance between your pinky and your thumb, that's basically the size that a single camera will be looking at the sky. More visually, any camera could be able to fit the Orion constellation in at any given time, and this means that basically after the entire survey, it'll be looking at about 400 million stars or so, all of which will have 30-minute cadence. This means we'll know what the star is doing every 30 minutes for about a month, which is pretty amazing. At Vanderbilt specifically, we've had to collate a bunch of catalogs from a variety of astronomers, which if you've tried to get a lot of information from a large number of astronomers, you know how difficult that is. But we've made it as homogeneous as possible, which is great because it's a catalog of basically the entire sky, which has not been done before. That information is actually found on Filtergraph, which is a great service. But the best thing about TESS is that there's actually no proprietary period on the science products. So the public and every group will actually be able to look at that data at the same time as a science team. And the satellite itself is launching on April 16th, so fingers crossed nothing goes wrong. But that's it.
I'm Tina King. I'm the librarian for science and engineering. Today I'm going to introduce some library services for your research life cycle. So this cycle, research life cycle, from the data generation to data analysis to data preservation. So the library helps you through the steps. So here I want to say the gray part, we consider short-term data storage, and the yellow part is the long-term storage, data storage. I will take examples. For example, we have services and the tools. Some of the tools are free, and some of the tools, our library have subscription with it. For example, the monthly, we have subscription of institutional subscription. We can help you with it. And yesterday, we have a seminar talking about the research data management tools, DMP tools, to teach you how to write your data management plan with that tool, which we have subscription with that too. And also on the left side, we have the Discovery Archive with our institutional repository where you can deposit your data and save your research on.
Hello, my name is Jorge Salas. I'm an alumni from the physics department. I'm now working with an interdisciplinary group for Professor Goodwin, and we're studying here, reading behaviors, well, essentially, what I want to show you here is something related to studying how people highlight on digital formats and on paper formats. So what we did here, we took 500 middle school students. We gave them a reading test, which was half in digital format, half in paper format, and allowed them to highlight. And then we used our software, and we classified the highlighted text. After a while of cleaning, took many weeks, we classify in terms of words or sentences or phrases, collocations, how they highlighted. Well, we can show here a sample to show many common trends. We see some differences, but here, important thing we find is that many students find themselves deterred from highlighting when they're in digital formats compared to paper formats. This is still an ongoing work because we're coupling this to some eye tracking data that we have, which requires also a lot of cleaning. And we're also comparing this to comprehension. We're studying also grammatical structures. It's, well, we have a lot of statistical modeling here. So, thank you very much.
Good morning. My name is Hong Yang. I'm a research faculty in electrical engineering and computer science. I'm going to talk to you about performance today. Is performance your problem? For example, are your clothes running too slowly? or you'll sometimes find that your big data workflows are stalled, or do you want to computationally test a hypothesis, but you don't know how to do that yet. So in that case, we may have solutions for you. We are building a scalable computing lab in our department in which my colleagues and I have been working on data science, and we are looking for collaborations with all kinds of data scientists across campus. And we use our tools, our expertise in high-performance computing and predictive modeling. So what can we do? Really, performance is our business. We can help you speed up your computational workflows through all kinds of parallel processing. We can also make big data analytics go fast through some kind of scheduling techniques. We can also bring predictive power through new models and algorithms. So if you are having a problem with the performance, we'll be happy to work with you. Thank you.
Remember, next one, where's the microphone? So we have noon, we start to have this panel discussion. So we have about 17 minutes. You have your bio break, and don't forget, bring your lunch back. Andrew.